Now, let's move on and say, okay, we are now going to assume that all gases that don't have vapor domes. So we're going to assume that water vapor, ammonia vapor, propane vapor, R134A vapor, and R22 vapor, those gases don't act as ideal gases. Okay? Those gases don't. Anything that has a vapor dome, it's not going to act as an ideal gas. We'd have to use a generalized compressibility chart. But common gases, nitrogen, oxygen, carbon dioxide, all of those things are going to be considered, we could assume to be ideal gases. The things that are gaseous in every situation every common situation. Okay? When we look at that, we are going to make the assumption. So I'm going to say assume that carbon dioxide or carbon monoxide, carbon dioxide, oxygen, nitrogen, neon, argon, helium, those are going to be our common ideal gases, that these gases are ideal. And so they're going to follow this equation, PV is equal to RT. Okay. Now, once we make and we say that we're following the ideal gas model, and something else happens. When we say that we're following this model, remember, we have to have two things to set the state. Always two things to set the state. If we say we're going to follow the ideal gas model, that's really the one thing. We're following the ideal gas model. And then the only other thing we need is we're going to say that the properties are a function of temperature only. Okay, so all we need is the temperatures. And so, if we go to our document camera, and we're now look at table A22, which is the ideal gas properties of air. Now we're assuming that this gas is an ideal. Okay, and we're going to look at here ideal gas properties of air. You can see now that these properties are all given by the temperatures. We don't have to look at temperatures and pressures. We're just going to look by temperatures. Here's all our nice temperatures. These are in absolutes. See, there's going to say temperatures in Kelvin. And they're going to show you what the enthalpy is first and the internal energy is second. This is different than our earlier tables with our steam tables that substances that have vapor domes. They always gave you internal energy first and then enthalpy second. This flips the order of them. Note how it goes. It gives you all the temperatures. They go all the way down here to 440, and then there's a second column over here that starts at 450. Okay? Goes all the way down here to the bottom to 740, and then we go to the next page. Right now, the only thing that we're going to be looking at are these first three columns. This column and these two columns here are not, you can't use them right yet, because these deal with something called entropy that we won't talk about until chapter 6. However, on exam, sometimes students trying to find out what the pressure or the specific volumes are use these numbers, and it's completely wrong. So don't use these. Don't use these. Right now, just use the first three columns. Just use the first three columns. So we're following the ideal gas model, and now we can look up properties with ideal gas model. We can look them up for internal energy and enthalpy. We can look them up in tables. Okay, that's been provided to us in our textbook. Okay, so let's look at the ideal gas model. We said that PV is equal to RT. Okay, we said that internal energy is now a function of temperature. It's not times temperature, it's a function of temperature alone. That's our one thing. The ideal gas model is our second thing. That's the two things we need to set our state. So enthalpy, which is equal to internal energy, which is now only a function of temperature, plus PV. Okay, U plus PV is equal to enthalpy. Well, now we're dealing with the ideal gas. Look what happens. PV is equal to RT. And so we can write that, or it's equal to internal energy plus RT. And that's how we can define enthalpy in this state. Now, ideal gas model is a model. We are probably not, the gases that I said to assume are ideal gases probably don't have a compressibility factor of exactly 1. So when we're modeling them as an ideal gas, we are saying I am going to accept a little bit of error. I'm going to model the gas as ideal because it simplifies my calculations a lot. I can say Z is equal to 1. I don't have to look things up in that generalized compressibility chart. And the error might be, 1 or 2% from the real answer. Okay, so note that when you say that you're using the ideal gas model, you're automatically telling somebody, hey, I'm modeling at this because there's an acceptable amount of error that I'm putting into my calculations, but it's not a big amount of error. It's a very small amount of error. Okay, we have some tables for to find properties for air is a primary ideal gas that we're going to deal with. But we also have on page table A23, we have properties of carbon dioxide, carbon monoxide, water vapor, oxygen, and nitrogen. And so right now, you can find these properties here. And notice that in these properties, they give you the properties not on a mass basis, but they give this to you on a molar basis. These are in a molar basis. Okay, air, they give it to you on a mass basis. But the carbon dioxide, carbon monoxide, they give you these properties on a molar basis. Okay. Now, ideal gas model that we're going to follow there might be some other models that will give us less error, but more complexity. So again, we're going to follow that model and keep going down that. Now, there's one more thing I want to talk about today as we get talking about and ending up this topic about ideal gases. And I'll get to that in the next video.